What if everything you know about how the universe began is just the tip of the iceberg? Picture this: a single, unimaginably hot and dense point, smaller than an atom, suddenly expanding faster than the speed of light, giving birth to everything we see today. That's the Big Bang, the story we're all familiar with. But here's the thing: scientists have uncovered secrets about that explosive moment and the eerie period right after it, called cosmic inflation, that will completely reshape how you think about reality. These aren't just small updates, they're revelations so profound they challenge our very understanding of time, space, and existence itself. And today, we're diving into 25 of the most incredible discoveries that have shaken the foundations of cosmology. Think about the last time you looked up at the night sky and felt that humbling sense of wonder. Those tiny points of light are more than just stars, they're fragments of a story written in the fabric of the cosmos, a story that started nearly 14 billion years ago. For decades, astronomers and physicists have pieced together clues hidden in the faint glow of ancient radiation, the dance of galaxies, and even the quantum quirks of particles smaller than we can fathom. And what they've found goes far beyond textbooks. Some of these discoveries suggest that our universe might be just one bubble in an infinite cosmic foam, while others hint at mysterious forces that stretched space itself like taffy in the blink of an eye. This isn't just science, it's a detective story on the grandest scale imaginable. Every new breakthrough peels back another layer of the mystery, revealing twists no one saw coming. From mind-bending evidence that the universe is far larger than we ever thought, to hints of other universes lurking beyond our reach, these discoveries don't just answer old questions, they spark new ones that are even wilder. So whether you're a space enthusiast or just someone who loves a good cosmic puzzle, buckle up. By the end of this journey, you'll see the Big Bang and our place in the universe in a whole new light. One of the most astonishing confirmations of the Big Bang theory came from a pair of astronomers who weren't even looking for it. In 1964, Arno Penzias and Robert Wilson were tinkering with a giant radio antenna in New Jersey, trying to eliminate mysterious static interfering with satellite communications. No matter how much they cleaned the equipment or adjusted settings, that faint hiss persisted, coming from every direction in the sky. What they'd stumbled upon wasn't a technical glitch, but something far more profound: the cosmic microwave background. This faint whisper of radiation, barely 3 degrees above absolute zero, turned out to be the oldest light in the universe, stretched and cooled over billions of years into microwave wavelengths. It's the afterglow of the Big Bang itself, lingering like the heat from a fading ember. This discovery was the smoking gun cosmologists had been waiting for. If the universe began as a superheated explosion, scientists reasoned that energy would still echo through space, growing fainter as the cosmos expanded. The CMB matched those predictions perfectly, but here's where it gets even stranger. When satellites like Cosmology and Planck mapped this radiation in exquisite detail, they found it was almost perfectly uniform, same temperature in every direction, down to 1 part in 100,000. That uniformity is mind-boggling. How could regions of the universe now billions of light-years apart, which could never have exchanged heat or information, be so precisely matched? This puzzle led to one of the wildest ideas in cosmology: cosmic inflation. The theory suggests that in the first sliver of a second after the Big Bang, space itself expanded exponentially faster than light, smoothing out all irregularities like stretching a crumpled sheet of paper. The CMB's near uniformity is one of inflation's strongest clues, a snapshot of the universe before gravity had time to clump matter into galaxies and stars. But the story doesn't end there. Tiny fluctuations in the CMB, slightly warmer or cooler patches, are like cosmic fingerprints. They're the seeds of everything we see today, the blueprints for galaxy clusters and the vast cosmic web. Without those microscopic wrinkles in space-time, our universe would be a featureless void. Penzier's and Wilson's accidental hiss revolutionized our understanding of the cosmos. It's a reminder that sometimes the universe's greatest secrets hide in plain sight, waiting for someone to listen closely. But while the cosmic microwave background revealed the Big Bang's afterglow, it was another discovery that showed the universe wasn't just born in a fiery explosion, it's still stretching outward at this very moment. Enter Edwin Hubble, the astronomer who peered into the night sky and saw something no one expected. In the 1920s, Hubble noticed something peculiar about the light from distant galaxies. It wasn't behaving the way it should. Instead of shining at the wavelength scientists predicted, the light from these galaxies appeared shifted toward the red end of the spectrum, as if the universe itself were tugging at the light's fabric. This phenomenon, called redshift, wasn't just a curiosity, it was a cosmic clue. Hubble realized that the farther away a galaxy was, the more its light was stretched, like a siren's pitch dropping as it speeds away. And that could only mean one thing: the universe wasn't static as everyone had assumed. It was expanding, carrying galaxies along with it like raisins in a rising loaf of bread. Hubble's groundbreaking observation led to what we now call Hubble's law, the idea that a galaxy's distance and its speed of movement are directly linked. The faster a galaxy races away from us, the farther it must be, a relationship quantified by the Hubble constant, a number that tells us how quickly the cosmos is growing. But here's where it gets even more fascinating. By measuring the Hubble constant, scientists could essentially rewind the universe's expansion like a film in reverse, tracing everything back to that singular, hot, dense moment, the Big Bang. This wasn't just theoretical math, it was real, observable evidence that the universe had a beginning, and the implications were staggering. If the cosmos is expanding today, it must have been smaller and denser in the past. Run the clock back far enough, and everything we see, every galaxy, every star, every atom would have been crushed together in a space smaller than a pinprick. Yet Hubble's law didn't just confirm the Big Bang, it also gave us a way to estimate the universe's age. By calculating how fast space is stretching, astronomers could approximate how long it's been since that initial explosion. Current estimates put the universe at roughly 13.8 billion years old, a number refined over decades by increasingly precise measurements of redshift and cosmic distances. But the Hubble constant isn't just a relic of the past, it's still a hotly debated figure today, with different methods yielding slightly different results, a discrepancy that hints there might still be gaps in our understanding of dark energy, the mysterious force accelerating the universe's expansion. Hubble's discovery transformed our cosmic perspective. It showed us that the universe isn't some unchanging backdrop but a dynamic, evolving entity, still bearing the fingerprints of its explosive birth. And every time we measure the light from a distant galaxy, we're not just observing the present, we're reading a chapter from the universe's grand, unfolding story. The universe didn't just burst into existence fully formed, it had to cook its first ingredients. In those first dizzying minutes after the Big Bang, the cosmos was a seething cauldron of energy so intense that even atoms couldn't hold together. But as the universe expanded and cooled, something remarkable happened. Protons and neutrons began to stick together, forging the very first atomic nuclei in a process called primordial nucleosynthesis. This brief window, lasting only about 17 minutes, left behind a cosmic recipe we can still read today, written in the oldest elements of all. Here's why this matters. The Big Bang theory makes a startlingly precise prediction. About 75% of the universe's ordinary matter should be hydrogen, 25% helium, and trace amounts of lithium. When astronomers measure the actual abundances of these elements in ancient gas clouds and distant stars, the numbers line up almost perfectly. It's as if the universe handed us a receipt from its earliest moments, one we're still decoding 14 billion years later. But how did this cosmic alchemy work? Picture the early universe as a particle accelerator hotter than the core of a star. In that chaos, protons and neutrons constantly collided, forming deuterium, a heavy isotope of hydrogen. Most of this deuterium was quickly smashed apart again by the intense heat, but as the universe cooled, some survived long enough to fuse into helium. The key was timing. If the universe had expanded even slightly faster, fewer neutrons would have been trapped, leaving less helium behind. Slower expansion would have meant more helium. The observed balance is like a tuning fork ringing at just the right pitch, confirming the exact conditions of the early cosmos. What's even more astonishing is how sensitive this process was. The amount of deuterium we see today acts like a cosmic thermometer, telling us the density of ordinary matter in the early universe. Too much matter and deuterium would have been destroyed. Too little and it wouldn't have formed at all. The fact that our measurements match the Big Bang's predictions so closely is like finding a fossilized raindrop and using it to calculate the exact atmospheric pressure of the ancient Earth. Yet primordial nucleosynthesis did more than just validate the Big Bang. It also hinted at something invisible. The total amount of ordinary matter we see in stars and gas clouds is far less than what the deuterium measurements suggest should exist. This discrepancy was one of the first clues that most of the universe's matter isn't the stuff we're made of. It can't interact with light, form atoms, or clump into stars. We now call it dark matter, and its shadowy presence was first glimpsed in the delicate balance of those first few elements. So when you look up at the night sky and see the glow of distant stars, remember this: every atom of hydrogen in those stars, every wisp of helium in a nebula, is a relic of those explosive first minutes. They're not just elements, they're time capsules, carrying secrets from a time before time had meaning. And the fact that we can read that story, written in the language of nuclear physics, is one of science's most breathtaking triumphs. Alan Guth was staring at a blackboard in 1979 when a radical idea struck him. What if the universe didn't just expand after the Big Bang, but exploded outward faster than light itself? This flash of insight, cosmic inflation, didn't just tweak the Big Bang theory, it solved two of cosmology's biggest mysteries in one swoop. The first, called the horizon problem, asks why opposite sides of the universe look so similar. If light hasn't had time to travel between them since the beginning, how could they sync up their temperatures so perfectly? The second, the flatness problem, is even stranger. No matter how we measure it, space appears almost perfectly flat, like a sheet of paper stretched taut. But in an expanding universe, this balance is as unlikely as a pencil standing on its tip for billions of years. Inflation answers both riddles with a dizzying proposition. Imagine the universe just a trillionth of a second old, suddenly ballooning 100 trillion times in size, faster than a snap of your fingers. This hyper-expansion would have smoothed out any wrinkles, explaining the CMB's eerie uniformity. It also stretched space so thin that any curvature became undetectable, like inflating a balloon until its surface seems flat. Guth's theory didn't just patch holes in the Big Bang, it rewrote the first chapter of cosmic history. But inflation wasn't just a neat idea, it left fingerprints. Quantum fluctuations during that explosive stretch would have been magnified into tiny density variations, the very seeds that later grew into galaxies. When telescopes like Planck mapped the CMB's subtle temperature differences, they found patterns matching inflation's predictions down to the smallest scales. It's as if we uncovered the universe's blueprints scribbled in the afterglow of its birth. Yet the wildest twist might be what inflation implies about reality itself. If space can stretch once, why not multiple times? Some theories suggest our universe is just one bubble in an endless froth of inflating cosmos, each with its own laws of physics. Guth's blackboard scribbles didn't just solve old puzzles, they opened doors to realms beyond imagination. The universe's grandest structures, galaxies, clusters, the entire cosmic web, owe their existence to the tiniest of triggers. During inflation's furious expansion, space wasn't just stretching smoothly. It was quivering with quantum fluctuations, microscopic ripples in the fabric of reality. These weren't mere vibrations but seeds of destiny, imperfections that gravity would later nurture into the architecture of everything we see. Think of it like blowing up a balloon covered in fine sand. As the balloon inflates, tiny grains create uneven patches, some spots slightly denser, others emptier. In the cosmos, those grains were quantum fluctuations, stretched to colossal scales by inflation's exponential growth. What began as subatomic flickers became regions where matter was ever so slightly more or less dense, differences measured in parts per 100,000. But over billions of years, gravity amplified these whispers into shouts. Denser patches pulled in more material, growing into galaxies, while lighter areas emptied out, forming the voids between them. The cosmic microwave background is our time machine to this pivotal moment. Those faint temperature variations, warmer spots where matter was denser, cooler spots where it was thinner, are direct snapshots of those primordial quantum ripples. Satellites like Planck have mapped these variations with astonishing precision, revealing patterns that match theoretical predictions almost perfectly. It's as if we're looking at the universe's fingerprint, its unique signature imprinted in the first fraction of a second. What's truly mind-bending is the scale of this transformation. Quantum mechanics typically governs the impossibly small particles dancing in uncertainty. Yet inflation magnified these quantum quirks to cosmic proportions, weaving them into the universe's very structure. Without those fluctuations, space would be a featureless void, devoid of stars, planets, or life. The Milky Way, Earth, even you, all exist because of quantum jitters frozen into spacetime during that fleeting inflationary burst. Recent simulations show how perfectly these initial conditions line up with what we observe today. When scientists input the CMB's fluctuation patterns into supercomputers and let gravity work its magic over billions of virtual years, the resulting cosmic web mirrors our actual universe with uncanny accuracy. It's a staggering validation that the largest structures trace back to the smallest possible origins. Yet mysteries remain. Some fluctuations appear slightly stronger or weaker than standard models predict, hinting at unknown physics during inflation. Could there have been multiple inflationary phases? Did other forces interact with quantum fields in ways we haven't yet imagined? Every new observation tightens the link between quantum mechanics and cosmology, suggesting that the key to understanding the vast universe lies in decoding the infinitesimal. In 2014, the cosmology world erupted with excitement over a discovery that seemed too good to be true, and as it turned out, it was. The BICEP 2 telescope at the South Pole claimed to have found the holy grail of cosmic inflation, primordial gravitational waves. These faint ripples in spacetime, predicted to arise from inflation's violent expansion, would leave a unique twist in the polarization patterns of the cosmic microwave background. The announcement made global headlines, hailed as definitive proof of inflation and a window into the universe's first trillionth of a second. Scientists compared it to hearing the faint echo of the Big Bang itself, but the celebration was short-lived. Further analysis revealed that much of the signal BICEP 2 detected came from an unlikely culprit, interstellar dust within our own Milky Way. The swirling magnetic fields of these dust grains mimicked the exact polarization patterns researchers were hunting for, creating a cosmic mirage. It was a sobering reminder of how easily the universe can deceive even our most advanced instruments. Yet while the detection itself was retracted, the episode wasn't a failure. It forced cosmologists to sharpen their methods, leading to collaborations like the Planck satellite cross-checking data with unprecedented precision. The pursuit of gravitational waves also revealed something profound. Science at its best is self-correcting. The BICEP 2 team's willingness to openly revise their claims when new evidence emerged exemplified the rigorous skepticism that drives real progress. Their work refined our understanding of galactic dust's interference, paving the way for next-generation telescopes that'll scan the CMB with even greater sensitivity. What makes this hunt so crucial is what gravitational waves could tell us about inflation's energy scale. Different theories predict different signal strengths, some wildly intense, others nearly imperceptible. Detecting them would narrow down which version of inflation actually occurred, or if something even stranger took place. The fact that we're able to debate these possibilities, to design experiments delicate enough to test them, shows just how far cosmology has come. We're not just reading the universe's history, we're learning how to interrogate it. So while Bicep 2's gravitational waves turned out to be dust in the cosmic wind, the search didn't end. It evolved. New projects like the Simons Observatory and future space missions are building on those lessons, armed with better tools to separate true primordial whispers from galactic noise. Sometimes in science, the most valuable discoveries aren't the answers we find, but the better questions we learn to ask. If the cosmic microwave background is the universe's baby picture, then the Planck satellite was the world's most powerful camera, capturing every microscopic wrinkle and dimple with staggering precision. Launched in 2009 by the European Space Agency, Planck spent 4.5 years scanning the entire sky, measuring temperature variations in the CMB down to millionths of a degree. This wasn't just an upgrade, it was a revolution. Where earlier missions like COBE and WMAP sketched the broad strokes, Planck revealed the fine brushwork, turning cosmic whispers into a clear, unmistakable voice. What made Planck extraordinary wasn't just its sensitivity but its range. Observing at 9 different frequencies, it could distinguish the CMB's true signal from the fog of foreground interference, dust, gas, and even the Milky Way's magnetic field. Imagine trying to hear a single violin in a symphony orchestra, then realizing you could isolate every instrument's pitch perfectly. That's the clarity Planck brought to cosmology. Its maps showed temperature fluctuations spanning just a few arcminutes, scales smaller than the moon's apparent size in the sky. These tiny ripples held the keys to the universe's deepest secrets. One of Planck's most headline-grabbing contributions was refining the universe's age. By analyzing the CMB's patterns with unprecedented accuracy, it pegged the cosmos at 13.8 billion years old, a figure now engraved in textbooks. But the real magic lay in how it narrowed the margins. Earlier estimates had uncertainties of hundreds of millions of years. Planck shrunk that to a mere 20 million. That's like measuring a human lifespan down to the minute. Yet age was just the beginning. Planck's data transformed our understanding of the universe's recipe, the exact mix of ordinary matter, and dark energy. The numbers it delivered were startlingly precise: 4.9% atoms, 26.8% dark matter, and 68.3% dark energy. These aren't rough guesses, but values pinned down to the decimal point, derived from how the CMB's fluctuations respond to gravity and expansion over billions of years. It's as if we cracked open the universe's ledger and found every column perfectly balanced. Perhaps most crucially, Planck put cosmic inflation to the test. The satellite's detailed maps revealed patterns in the CMB's fluctuations that matched inflation's predictions almost perfectly, particularly the way warmer and cooler spots were distributed across different angular scales. This wasn't just confirmation, it was a stress test, eliminating competing theories that couldn't reproduce those subtle fingerprints. The data even hinted at which flavors of inflation might be correct, favoring models where the inflationary field's energy changed slowly rather than in abrupt spikes. But Planck also delivered surprises. Some large-scale fluctuations appeared weaker than expected, while certain alignments in the data, dubbed anomalies, defied easy explanation. One particularly puzzling feature, called the cold spot, is a strangely frigid patch of sky larger than inflation's models predict. Could these be statistical flukes, or might they point to new physics, perhaps even evidence of other universes bumping against our own? While Planck couldn't answer definitively, it transformed these curiosities from fringe ideas into serious research questions. The mission's legacy isn't just in the data it collected, but in how it changed cosmology. Planck showed that the universe is both more knowable and more mysterious than we'd imagined. Every decimal place it added to our measurements tightened the constraints on theories, forcing physicists to sharpen their ideas or abandon them. And as its final data release in 2018 faded from the headlines, it left behind a challenge, a blueprint for future explorers to dig even deeper into the cosmic dawn. Planck didn't just map the afterglow of creation, it handed us the magnifying glass we'll use to read the next chapters. In 1998, astronomers made a discovery so shocking it turned cosmology upside down. By studying distant supernova exploding stars so consistent we call them standard candles, they found something impossible. These stellar beacons weren't just dimmer than expected, they were fading faster at greater distances, as if space itself were stretching faster over time. The universe wasn't just expanding, it was accelerating, propelled by some invisible force pushing galaxies apart. This wasn't just a new ingredient in the cosmic recipe, it was a phantom in the equations, an anti-gravity we now call dark energy. What makes dark energy so baffling is how eerily it echoes cosmic inflation. Both involve space expanding at dizzying rates, one in the universe's first moments, the other dominating its present era. But the differences are just as striking. Inflation was likely driven by a quantum field that decayed explosively, while dark energy behaves like a cosmological constant, its density remaining eerily steady as the universe grows. Imagine two chapters of the same story written in opposing ink. One a violent burst lasting fractions of a second, the other a slow, relentless pressure stretching across billions of years. The real twist, dark energy's dominance today might be inflation's ultimate legacy. Quantum fluctuations during that early hyper-expansion could have planted the seeds for dark energy's eventual takeover. Some theories even suggest dark energy is inflation's faint afterglow, a remnant of that primordial field that never quite switched off, yet the numbers defy intuition. Dark energy's measured strength is a factor of 10 to the power 120 smaller than quantum physics predicts. It's like expecting a tidal wave and finding a single molecule of water instead. This discrepancy hints at gaps in our understanding so vast they might require rewriting gravity itself. Could dark energy and inflation be two faces of the same phenomenon, separated by cosmic epochs? Or is the universe playing a deeper game we've yet to decipher? Every supernova we observe, every galaxy racing away, carries clues to this mystery, one that began with a bang and may end in a whisper. The idea that our universe might be just one bubble in an endless froth of others isn't science fiction, it's a serious possibility born from the mathematics of cosmic inflation. Picture this, if space could undergo that explosive stretching once, what's stopping it from happening over and over in countless regions, each spawning their own separate cosmos? This is the multiverse hypothesis, a breathtaking implication of eternal inflation, where the process that birthed our universe never truly stops. Instead, it becomes a self-replicating fractal, with new universes constantly budding off, each with its own unique physics, constants, and maybe even dimensions. What makes this idea so compelling is how neatly it solves some of cosmology's stickiest puzzles. Take the fine-tuning problem, the eerie precision of our universe's physical constants. If gravity were slightly stronger, stars would burn out in a blink. If weaker, galaxies would never form. In a multiverse, this perfection isn't a miracle but a statistical inevitability. With infinite variations, some universes would inevitably hit the cosmic jackpot, permitting life by pure chance. We find ourselves in one not because it's special, but because it's the only kind where beings like us could exist to ponder the question. Yet the multiverse isn't just a cosmic lottery, it's a battleground between science and philosophy. Critics argue that if other universes are permanently beyond our observation, does the hypothesis even qualify as science? Normally, a theory must make testable predictions, but how do you test the untestable? Ingeniously, physicists have proposed indirect signatures. Maybe colliding bubble universes left bruises in our cosmic microwave background, like fingerprints on a windowpane. The Planck satellite's anomalous cold spot has fueled speculation. Could it be a scar from such a collision? Others suggest that gravitational waves from inflation, if ever detected, might encode clues about the broader multiverse's structure. The philosophical stakes are even higher. A multiverse reshapes how we think about existence itself. If every possible universe exists, does that render our choices, our history, even our laws of physics, somehow less meaningful? Or does it amplify the wonder that in the vastness of all possibilities, we get to witness this particular cosmic story? The debate spills into theology, ethics, and even pop culture, revealing how deeply inflation's implications resonate beyond astrophysics. What's undeniable is how the multiverse hypothesis pushes science to its limits. It forces us to ask, what counts as evidence when the very nature of reality might hide most of itself from view? Whether the multiverse is real or not, its mere possibility has already expanded our imagination, proving that the universe or universes still holds mysteries no one saw coming. When scientists first mapped the cosmic microwave background in exquisite detail, they expected randomness, a scattered, symmetric pattern of hot and cold spots like static on an old television. Instead, they found something unsettling. Certain large-scale features in the CMB appear oddly aligned along a single axis, a peculiar directional preference nicknamed the axis of evil. This cosmic quirk defies standard inflationary models which predict uniformity in all directions. It's as if the universe has a hidden compass pointing toward some unseen structure beyond our observational horizon. The name itself, borrowed from a political phrase, captures how discomforting this discovery was. In a universe that's supposed to lack any special direction, these anomalies suggest a preferred orientation, like finding all the paintings in a gallery tilted slightly to the left. One prominent example is the quadrupole-octopole alignment, where the largest temperature fluctuations in the CMB seem to line up along a shared plane. Statistically, this arrangement is extraordinarily unlikely in an isotropic cosmos, with odds comparable to flipping a coin and getting heads 20 times in a row. Some theorists propose that these alignments might be relics of a pre-Big Bang era, imprints from processes that shaped the infant universe before inflation erased all traces. Could spacetime itself carry a faint memory of its origins, like wrinkles in a bedsheet that refuse to smooth out? Others speculate that the axis of evil hints at an even wilder possibility, that our universe collided with another bubble universe during inflation, leaving a gravitational bruise in the CMB's geometry. But before rewriting cosmology textbooks, scientists had to consider a humbler explanation: observational error. Dust in our own galaxy, instrument calibration quirks, or even the way data is processed could introduce artificial patterns. The Planck satellite's all-sky surveys were supposed to settle the debate, yet the anomalies persisted, albeit at lower statistical significance. This lingering ambiguity has split the scientific community. Skeptics argue that the human brain is wired to find patterns, even in noise, while proponents counter that dismissing oddities too quickly risks missing revolutionary clues. The debate cuts to the heart of how science navigates uncertainty. Do we adjust theories to fit anomalies or assume they'll vanish with better data? The axis of evil remains one of cosmology's most tantalizing loose ends, a whisper that the universe might still be keeping secrets from us. Whether it's a flaw in our models, our measurements, or a crack in cosmic symmetry itself, this mystery reminds us that the Big Bang story may have chapters we've yet to read. Imagine trying to measure the shape of an entire city while standing on a single street corner. That's the challenge astronomers face when determining the geometry of the universe. Yet through painstaking observations of the cosmic microwave background and the large-scale distribution of galaxies, scientists have reached a startling conclusion: our universe is flat. Not flat like a sheet of paper, but in the cosmic sense where parallel lines never meet, and the angles of a triangle always add up to exactly 180 degrees. This isn't just a quirky fact, it's a direct prediction of cosmic inflation, one that ties into the deepest mysteries of matter, energy, and the fate of the cosmos. The evidence for this flatness comes from multiple independent lines of investigation. The most precise measurements come from the Planck satellite's analysis of the CMB's temperature fluctuations. Think of these patterns as cosmic contour lines. Their spacing and angles reveal whether space curves positively like a sphere, negatively like a saddle, or remains perfectly flat. Planck's data fits the flat model with staggering precision, down to a margin of error of just 0.2%. That's like measuring the curvature of a football field and finding it deviates from perfect flatness by less than the thickness of a dime. But why does flatness matter? It all comes down to density. According to Einstein's general relativity, the universe's geometry is determined by the total amount of matter and energy it contains. There's a critical density akin to a cosmic balancing point, where the gravitational pull of all that stuff exactly counteracts the expansion. Falls short of that density, and the universe would curve outward in an open, saddle-like shape. Exceed it, and space would close in on itself like a giant sphere. The fact that we observe flatness means the universe's density is fine-tuned to that critical value with almost impossible precision. Here's where inflation provides the elegant solution. The exponential stretching of space during that initial burst would have smoothed out any primordial curvature, like inflating a balloon to such enormous size that even the most wrinkled surface appears flat. This explains why we don't see the universe bending back on itself. Inflation ironed out the wrinkles, locking in a geometry so flat that even after billions of years of expansion, it remains indistinguishable from perfect. Yet flat geometry isn't just about space, it's a portal to understanding the universe's composition. That critical density includes everything: ordinary atoms, dark matter, and the enigmatic dark energy. When cosmologists tally up all the visible and invisible contributions, they arrive at a number eerily close to 1, exactly as flatness demands, but the breakdown is the real shocker. Atoms, the stuff of stars, planets, and us, account for less than 5%. Dark matter makes up about 27%. The rest, dark energy, that mysterious force accelerating the expansion. Without this precise mix, the universe wouldn't be flat, and we wouldn't be here to measure it. The implications stretch beyond geometry. A flat universe suggests an infinite one, with space stretching endlessly beyond our observable horizon. It also hints at a grim future with dark energy dominant. This flat expanse will keep accelerating forever, eventually tearing apart galaxy clusters, stars, and even atoms in a distant but inevitable Big Rip. Yet for now, that perfect flatness stands as one of inflation's most profound legacies, a cosmic tightrope walk, balanced by forces we're only beginning to comprehend. One of the most frustrating gaps in our cosmic origin story is the absence of definitive proof for inflation's primordial gravitational waves. These faint ripples in space-time should carry imprints from the universe's earliest moments, a direct snapshot of space stretching faster than light. Yet despite decades of searching, they remain maddeningly out of reach. The challenge isn't just technical. It's a fundamental clash between theory and observation that's forcing cosmologists to rethink everything from detector sensitivity to inflation's very mechanics. The hunt centers on a subtle twist in the cosmic microwave background's polarization patterns. As gravitational waves from inflation propagated through the early universe, they would have left a distinctive swirling signature called B-mode polarization, like fingerprints pressed into the afterglow of creation. Catching this signal would be the smoking gun for inflation, but here's the catch. It's buried under layers of interference, galactic dust, magnetic fields, and even the lensing of light by later cosmic structures all mimic similar patterns, creating a cosmic hall of mirrors where every potential detection could just be dirty glass. This was the lesson of the Bicep 2 controversy. When researchers announced they'd found B modes in 2014, the excitement was palpable, until follow-up studies revealed the signal was largely dust from our own Milky Way. The episode exposed just how delicate this search is. Gravitational waves from inflation would produce B modes at large angular scales, while dust and lensing dominate at smaller ones. Teasing them apart requires not just better telescopes but multi-frequency observations to filter out every contaminant. Yet the absence of a clear signal isn't necessarily bad news. It's forcing scientists to confront inflation's diversity problem. The theory comes in countless flavors, some predicting roaring gravitational waves we should have easily detected by now, others whispering so faintly they're practically silent. The fact that we haven't found them yet suggests inflation might have been lower energy than many models assumed, or that it unfolded in ways we haven't yet imagined. This is where upcoming experiments like LISA, the Laser Interferometer Space Antenna, could rewrite the rules. Unlike ground-based detectors that catch high-frequency waves from black hole collisions, LISA's space-based system will hunt for ultra-low-frequency ripples with wavelengths so vast they span light years. Some theories suggest these could include echoes from inflation's final moments, a cosmic bass note lingering beneath the universe's symphony. The stakes couldn't be higher. Finding primordial gravitational waves would cement inflation's place in cosmic history, while their continued absence might mean the universe's first moments were even stranger than we thought. Either way, this search is more than technical. It's a test of whether we can hear the faintest whispers of time's beginning. At first glance, the Big Bang theory's predictions for light element formation seem almost too perfect. Hydrogen and helium abundances match observations with uncanny precision. But there's a stubborn outlier in this cosmic recipe: lithium. According to primordial nucleosynthesis calculations, there should be about 3 times more lithium-7 in the universe than what we actually detect in ancient stars. This glaring mismatch, known as the lithium problem, has haunted cosmologists for decades, revealing cracks in our otherwise pristine understanding of the universe's first moments. The mystery isn't just about numbers, it's a clue that something fundamental might be missing from our models. Lithium-7 forms through a delicate chain of nuclear reactions in the early universe's fiery cauldron. First, helium-4 nuclei collide with tritium, a heavy hydrogen isotope, creating lithium-7. But here's the catch. This process competes with another reaction where beryllium-7, lithium's unstable sibling, captures an electron and decays into lithium. The predicted final abundance hinges on precise balances between temperature, density, and the lifetimes of these fleeting particles. The fact that real observations fall so far short suggests either our nuclear physics is incomplete or the early universe's conditions weren't quite what we've assumed. One proposed solution involves hypothetical particles called actions, which might have siphoned off energy during nucleosynthesis, subtly altering reaction rates. Another theory posits that primordial black holes evaporating in that first chaotic minute could have injected extra radiation, disrupting lithium's formation. Even more radical is the idea that some lithium gets burned inside stars over billions of years, though this struggles to explain why the discrepancy appears even in the oldest, most pristine stellar populations. What makes the lithium problem so tantalizing is its potential to unveil new physics. If standard cosmology can't account for this anomaly, perhaps it's a signpost pointing toward phenomena we've yet to discover: particles, forces, or even phases of the early universe that left no other trace. It's a reminder that even our most successful theories might be approximations, waiting for the next breakthrough to reveal a deeper layer of cosmic truth. For hundreds of millions of years after the Big Bang, the universe was a vast, featureless sea of neutral hydrogen gas, dark, quiet, and waiting. Then came the spark. Somewhere in that cosmic gloom, the very first stars ignited, their ultraviolet light slicing through the primordial fog like a match struck in a cavern. This was the dawn of the epoch of reionization, the moment when the universe woke up and became transparent. But how do we know about this pivotal chapter, one that left no direct starlight for us to see? The answer lies in subtle fingerprints pressed into the cosmic microwave background's polarization, a ghostly record of when everything changed. The process was anything but gentle. Those first stars, called Population 3, were behemoths hundreds of times more massive than our Sun, blazing with such intensity that their radiation ripped electrons from hydrogen atoms, ionizing the gas around them. As more stars and early galaxies formed, their combined ultraviolet output created expanding bubbles of ionized plasma, like ink dissolving in water. Eventually, these bubbles overlapped, flooding the entire universe with light and ending the so-called cosmic dark ages. Remarkably, we can still detect echoes of this transformation today. When the CMB's light photons last scattered off electrons just before the universe became neutral, they left a telltale imprint in their polarization patterns. But as those electrons were later pried loose during reionization, the CMB photons experienced one final interaction, a subtle twist in their polarization direction. By measuring this effect, satellites like Planck have pinned the timing of reionization to roughly 500 million years after the Big Bang. It's as if we're reading the universe's diary entry from its adolescence. Now the James Webb Space Telescope is turning those faint clues into a vivid picture. JWST's unprecedented infrared vision has spotted galaxies from this very epoch, small, chaotic, and furiously forming stars. The surprise, many appear brighter and more evolved than models predicted, suggesting reionization might have started earlier and progressed faster than we thought. Some even show evidence of supermassive black holes already in place, adding new layers to the mystery of how structures emerged so quickly after the Big Bang. What's emerging is a story of cosmic upheaval. The epoch of reionization wasn't a single event but a turbulent phase, with ionizing radiation bursting through the cosmos in fits and starts. Some regions became transparent early, while others held out like islands of neutral hydrogen. This patchwork process left scars we can still map in the CMB's polarization, a testament to the universe's growing pains. JWST discoveries are forcing us to rethink the engines behind reionization. Were massive stars the sole architects, or did black holes and galactic winds play a bigger role? Each new observation peels back another layer, revealing how the universe's first light didn't just illuminate space, it shaped everything that followed. Without this violent rebirth, the cosmos would still be shrouded in darkness, and we wouldn't be here to trace its glow across the ages. One of the most pressing mysteries in modern cosmology isn't about the universe's distant past, it's unfolding right now. Scientists call it the Hubble tension, and at its heart lies a simple question: how fast is the universe expanding today? The problem: two of our most trusted methods for measuring this rate, the Hubble constant, keep giving different answers, and the gap between them is widening with every new observation. It's as if two identical clocks, built to track time perfectly, started ticking at different speeds, forcing us to question whether we've misunderstood the mechanisms behind them. The first method relies on the cosmic microwave background, that ancient light from the universe's infancy. By analyzing the CMB's subtle fluctuations with missions like Planck, scientists can extrapolate how fast space should be expanding now, given 13.8 billion years of cosmic evolution. This approach gives a Hubble constant of around 67 kilometers per second per megaparsec, meaning for every million parsecs of distance. a galaxy moves away 67 kilometers faster each second. But then there's the second method, which looks at the universe's present-day anatomy. Astronomers use pulsating stars called cepheids and cataclysmic supernova as standard candles to gauge distances to nearby galaxies. By comparing these distances to the galaxy's redshifts, how much their light is stretched by cosmic expansion, they calculate the Hubble constant directly. The result, 73 kilometers per second per megaparsec. That difference might seem small, but over cosmic scales, it's a glaring discrepancy. At first, researchers brushed it off as measurement errors, but as techniques improved, the gap stubbornly refused to close. What makes this tension so electrifying is what it implies. If both methods are correct and each has been cross-checked relentlessly, then our understanding of the universe's composition or behavior must be incomplete. Maybe dark energy isn't constant but evolves over time, subtly altering the expansion rate. Or perhaps there's an unknown particle, like a lightweight neutrino variant, zipping through space and tweaking the cosmic balance. Some theorists even speculate that gravity itself might behave differently on large scales, a cosmic curveball that would rewrite Einstein's rules. The Hubble tension isn't just academic, it's a potential gateway to discoveries beyond the standard model of cosmology. Just as the orbit of Mercury revealed gaps in Newtonian physics, leading to general relativity, this discrepancy might be the universe nudging us toward something revolutionary. New telescopes like the Vera C, Rubin Observatory and the Nancy Grace Roman Space Telescope are joining the hunt, armed with sharper tools to scrutinize both distant supernova and the CMB's finer details. Whether the solution lies in exotic physics or hidden systematic errors, one thing's certain: the Hubble tension has turned a routine measurement into a high-stakes cosmic whodunit. And like all great mysteries, it's reminding us that the universe still has a few tricks up its sleeve. Buried in the cosmic microwave background's subtle temperature tapestry lies an anomaly so peculiar it has sparked debates ranging from cosmic defects to parallel universes. Dubbed the cold spot, this region of the CMB is significantly cooler than its surroundings, stretching nearly 1.8 billion light-years across, a void so vast it defies standard inflationary explanations. At first glance, it might seem like a statistical fluke, but the odds of such a cold patch appearing randomly are less than 2%. This isn't just a cosmic oddity, it's a potential crack in our understanding of the universe's infancy. One leading theory suggests the cold spot could be a relic of a cosmic texture, a topological defect left over from phase transitions in the early universe. Picture space itself as a fabric cooling from an ultra-hot state. As it transitions, tiny knots or wrinkles might form, like imperfections in ice as water freezes. These textures, predicted by some grand unified theories, could create gravitational wells so deep that light passing through loses energy, appearing cooler when we detect it billions of years later. If true, the cold spot would be a frozen fingerprint of physics operating at energies trillions of times higher than anything our particle colliders can reach. But the wilder hypothesis, and the one that captures imaginations, is that this anomaly might be a bruise from a collision with another bubble universe during inflation. In the multiverse scenario, our cosmos isn't alone but one of countless bubbles in an ever-expanding quantum foam. If a neighboring universe brushed against ours in that frenzied early expansion, the energy released could have left a localized chill in the CMB, like a cosmic kiss imprinted on the sky. Proponents point to the cold spot's unusual shape and its surrounding temperature patterns as possible signatures of such an encounter. Skeptics, however, argue for more mundane explanations. The cold spot might simply be a vast supervoid, a region of space unusually devoid of galaxies and matter. Light traveling through such a void would lose energy due to the universe's accelerated expansion, a phenomenon known as the integrated Sachs-Wolf effect. Yet surveys mapping galaxy distributions in the cold spot's direction reveal no void large enough to account for the temperature drop. This leaves astronomers in a quandary. If it's not a void and not a statistical glitch, what exactly are we looking at? The Planck satellite's detailed maps added fuel to the fire. While they confirmed the cold spot's existence, they also revealed strange secondary features, peculiar polarization patterns, and unexpected alignments in the surrounding CMB fluctuations. These nuances don't neatly fit any single theory, hinting that the truth might be stranger than anything we've yet imagined. Future missions like the Simons Observatory aim to scrutinize the cold spot with even sharper resolution, searching for telltale distortions that could distinguish between a cosmic defect, a multiverse collision, or something entirely new. What makes the cold spot so compelling isn't just its mystery, it's the reminder that even our best cosmological models might be incomplete. Whether it's a relic of higher dimensional physics, a window into the multiverse, or simply a fluke we've overinterpreted, this enigmatic patch of sky challenges us to ask, what else might be hiding in the CMB's whispers, waiting to rewrite the story we think we know? The first second after the Big Bang wasn't just the beginning of time. It was a cascade of transformations so rapid they make the blink of an eye feel glacial. Let's peel back those layers one by one. The earliest moment we can meaningfully describe is Planck time 10 to the power of -43 seconds. At this unimaginable threshold, all four fundamental forces of nature were fused into one unified superforce. Gravity hadn't yet separated from the quantum froth, and the concepts of space and time as we know them simply didn't exist. This was the ultimate singularity, where our current physics reaches its breaking point. By 10 to the power of -36 seconds, something spectacular happened. The universe underwent a phase transition like steam condensing into water, and gravity split off from the other forces. This unleashed cosmic inflation, sending space expanding exponentially faster than light. In less time than it takes for a photon to cross a single proton, the cosmos ballooned from quantum scales to something the size of a grapefruit, but inflation wasn't smooth. Quantum fluctuations got stretched to cosmic proportions during this stretch, planting the seeds for all future galaxies. Then, at around 10 to the power of -12 seconds, the universe was hot enough to cook up particles we can now only create in giant colliders, some 20 trillion degrees Celsius. This was the era of quark-gluon plasma, a seething primordial soup where quarks and gluons roamed freely instead of being locked inside protons and neutrons. Imagine a world where matter wasn't yet matter, just a churning ocean of fundamental ingredients too energetic to stick together. The next critical threshold came at 1 microsecond, when the universe cooled enough for quarks to finally bind into hadrons, protons, and neutrons through the strong nuclear force. But this wasn't a clean process. For every billion antiquarks annihilating with quarks, one quark survived. That tiny imbalance is why we have atoms, planets, and life today. Lose that one in a billion edge, and the universe would be nothing but light. By the time the clock struck 1 second, neutrinos decoupled from matter, streaming freely through space as they still do today. These ghostly particles now form the cosmic neutrino background, an even fainter cousin to the CMB that we've yet to detect directly. Meanwhile, protons and neutrons began fusing into deuterium and helium nuclei, kicking off primordial nucleosynthesis, the universe's first atomic cookbook. What's breathtaking about this timeline isn't just its precision, but how fragile each step was. Alter inflation's duration by a fraction of a second, tweak the quark-antiquark ratio slightly, and stars, galaxies, everything might never have formed. The first second wasn't just the universe's violent birth. It was a precision ballet where every step had to be perfect for us to exist at all. Dark matter is the invisible architect of the cosmos, sculpting the universe into the web of galaxies and clusters we see today. While inflation set the stage by stretching quantum fluctuations into cosmic ripples, It was dark matter's gravitational embrace that turned those blueprints into reality. Imagine the early universe as a vast construction site where ordinary matter, the atoms that make up stars and planets, was like dust in the wind, too lightweight to clump together on its own. But dark matter, unaffected by light or heat, acted as the scaffolding, pulling matter into its gravitational wells and knitting the cosmos into structure. Here's the key: without dark matter's gravitational anchor, the universe would look drastically different. Inflation's quantum fluctuations created tiny density variations, but those alone couldn't explain how galaxies formed so quickly after the Big Bang. Ordinary matter, buffeted by radiation pressure, would have taken much longer to collapse into stars and galaxies. Dark matter, though, doesn't interact with light, it feels only gravity. So while atoms were still bouncing off photons in a chaotic dance, dark matter was already quietly pooling into vast halos, creating gravitational pits where ordinary matter could eventually settle. We see the proof in the cosmic web itself. Simulations of the universe's evolution, factoring in dark matter's influence, produce filamentary structures eerily similar to what telescopes observe. These dark matter filaments stretch across billions of light years, funneling gas and galaxies into sprawling clusters and voids. Even more telling is the way galaxies rotate. Their outer stars whirl far faster than visible matter alone can explain, as if gripped by some unseen hand. That hand is dark matter's gravity, holding galaxies together like invisible glue. Yet the story isn't just about structure, it's about timing. Dark matter's early dominance allowed galaxies to form while the universe was still young, seeding the first stars hundreds of millions of years earlier than pure atomic models predict. This timeline aligns perfectly with what the James Webb Space Telescope now observes: surprisingly mature galaxies flickering to life in the cosmic dawn. Without dark matter's head start, these ancient behemoths shouldn't exist. The irony is profound. The same substance that makes up 85% of the universe's matter remains almost entirely hidden from us. We map its presence indirectly through gravitational lensing, galaxy motions, even the bending of the cosmic microwave background. But every detection method circles back to the same conclusion. Dark matter's gravity wrote the rulebook for cosmic construction, while ordinary matter merely filled in the details. This invisible force didn't just shape the past, it's shaping the future. Dark matter's gravitational pull continues to steer galaxies into collisions, fueling star formation and black hole growth billions of years from now. It's the silent director of the universe's grand narrative, invisible yet indispensable, turning inflation's subtle whispers into the symphony of structure we call home. In the blink of a cosmic eye, the universe shifted from exponential expansion to the fiery chaos we call the Big Bang. But how did this transition happen? Inflation didn't just gently wind down. It ended in a spectacular burst of energy that transformed the cold, stretched quantum fields into a seething plasma of particles. Think of it like a frozen lake suddenly cracking apart, releasing all the pent-up energy beneath its surface in one violent instant. This moment, known as reheating, marks where inflation's abstract physics gave way to the tangible universe we recognize today. The key to understanding this shift lies in the inflaton field, the hypothetical quantum field responsible for driving cosmic inflation. As the universe expanded, this field didn't just stretch space, it stored enormous potential energy like a coiled spring under unimaginable tension. Eventually, that energy had to go somewhere. When inflation reached its natural endpoint, the inflaton field began oscillating wildly, transferring its energy to the surrounding quantum soup. These vibrations didn't just dissipate, they created particles, quarks, electrons, photons flooding the cosmos with heat and light for the first time. Reheating wasn't a smooth process. Some regions of space might have transformed earlier than others, creating temporary pockets of extreme temperature differences. Picture boiling water in a pot before reaching equilibrium. bubbles of hot and cold roil chaotically. Similarly, the early universe likely went through localized bursts of particle creation before settling into the uniform inferno we see in the cosmic microwave background. The sheer violence of this phase would have generated gravitational waves, ripples in spacetime that future observatories might still detect as faint echoes of inflation's dramatic finale. What's fascinating is how delicately balanced this transition had to be. If reheating had released even slightly more energy, the universe might have been too dense for galaxies to form. Too little, and matter would have spread too thin to clump together. The fact that we exist at all suggests this process struck a perfect equilibrium, one that turned abstract quantum physics into the concrete building blocks of reality. Some theories propose even wilder scenarios. Could reheating have left behind exotic relics like primordial black holes or hidden particles that still lurk in the cosmos today? Others suggest the inflattened field didn't vanish completely but lingers as dark energy, subtly shaping the universe's fate billions of years later. The end of inflation wasn't just a boundary in cosmic history. It was the spark that set everything else in motion, a moment where potential became reality in a blaze of creation. Stephen Hawking and James Hartle once posed a question that sounds like a riddle. What if the universe has no edge in space and no beginning in time? Their no-boundary proposal is one of the most radical reimaginings of the Big Bang's origins, merging quantum weirdness with cosmic birth in a way that dissolves the singularity altogether. Picture the universe not as a fiery explosion from nothing, but as a smooth, four-dimensional curve where time behaves like space, a geometry with no sharp edges, no boundaries, and no definitive starting point. It's like asking what's north of the North Pole. The question itself loses meaning. This idea flips traditional cosmology on its head. Instead of a singular moment of infinite density, the no-boundary condition suggests the early universe was more like a rounded-off sphere at the bottom of time. As you trace the cosmos backward, time transitions smoothly into a dimension that behaves like space, evading the need for a singularity. Think of it like Earth's South Pole. There's no south of the South Pole, just a point where all lines of longitude converge. Similarly, in Hawking and Hartle's model, the Big Bang isn't a violent beginning but a natural feature of a self-contained universe, where asking what came before becomes as nonsensical as asking what's beyond the universe's spatial edges. The magic lies in quantum mechanics. At scales smaller than atoms, particles defy classical logic, existing in smeared-out probabilistic states. Hawking and Hartle applied this quantum fuzziness to the entire cosmos, proposing that the universe's earliest moment was a superposition of all possible configurations, a quantum blur that only crystallized into classical spacetime as it expanded. This blending of quantum physics and general relativity offers an elegant escape from the infinities that plague traditional Big Bang models, replacing the singularity with a finite yet boundless geometry. Critics argue the proposal is more metaphysical than testable, but subtle clues might lurk in the cosmic microwave background. If the universe truly had no boundary, its quantum origins could have imprinted unique statistical patterns on the CMB's fluctuations, anisotropies that future telescopes might one day detect. Others suggest gravitational waves from the universe's quantum phase could carry signatures of this smooth transition, though separating them from later cosmic noise remains a monumental challenge. Beyond equations, the no-boundary proposal reshapes how we think about existence. It implies the universe didn't begin in any conventional sense but emerged from a timeless quantum state, sidestepping the need for a creator or external cause. For Hawking, this was the ultimate triumph of physics, a theory where the universe could explain itself, finite yet unbounded, like a cosmic Ouroboros swallowing its own tail. Whether the math ultimately matches reality or not, the idea stands as a testament to human imagination, our audacity to rewrite the origin of everything. Hidden in the sprawling cosmic web of galaxies lies a ghostly imprint, an echo from the universe's infancy, frozen in time. These are baryon acoustic oscillations, vast ripples in the distribution of matter that stretch across hundreds of millions of light years. Imagine dropping a stone into a pond, watching the ripples spread outward, then instantly freezing the water solid. That's essentially what happened to the universe when it was just 380,000 years old, locking these primordial sound waves into the very fabric of space. The story begins in the seething plasma of the early cosmos, a dense soup where protons, electrons, and photons were locked in a violent dance. Gravity pulled matter inward, while radiation pressure from photons pushed outward, creating a tug of war that generated sound waves, literal compressions and rarefactions traveling through the hot plasma at half the speed of light. These weren't sound as we know it, but rhythmic density variations like cosmic bass notes thumping through the universe. When the plasma cooled enough for atoms to form during recombination, photons finally broke free, creating the cosmic microwave background. But the sound waves didn't vanish. They left behind a fingerprint, an invisible spherical shell of matter, roughly 500 million light-years across, marking the distance those waves had traveled before freezing. Today, we detect these frozen echoes by mapping millions of galaxies. Surveys like the Sloan Digital Sky Survey reveal a curious pattern. Galaxies are slightly more likely to be found at a specific distance from one another, clustering on the surface of those ancient bubbles. It's as if the universe is a vast orchestra, with every galaxy sitting where a musical note once resonated. This predictable scale, called the sound horizon, acts as a cosmic ruler, allowing astronomers to measure distances across the universe with astonishing precision. But baryon acoustic oscillations aren't just relics, they're powerful tools for probing dark energy. By comparing how these ripples appear in nearby galaxies versus those billions of light-years away, scientists can track how the universe's expansion has accelerated over time. The spacing between galaxies in these oscillations reveals whether dark energy has been constant or evolving, a clue that could crack open one of cosmology's biggest mysteries. What's breathtaking is how these subtle patterns connect the universe's birth to its present structure. Those frozen sound waves didn't just shape where galaxies formed, they're still guiding our understanding of cosmic evolution today. Every time astronomers measure the clustering of distant quasars or map the distribution of galaxy clusters, they're tuning in to a frequency set in motion when the universe was a newborn, its first cries etched forever in the stars. While the cosmic microwave background captures most of the spotlight, there's an even older and more elusive whisper from the dawn of time, the cosmic neutrino background. Born just 1 second after the Big Bang, these ghostly particles have been streaming through the universe almost completely undisturbed for nearly 14 billion years, carrying secrets from a time when the cosmos was still an inferno of pure energy. Imagine trying to catch a shadow. Neutrinos interact so weakly with matter that trillions pass through your body every second without a trace, making their ancient background radiation far harder to detect than the CMB's glow. The story of these relic neutrinos begins during the universe's violent adolescence. When temperatures soared above 10 billion degrees, neutrinos were trapped in constant collisions with protons, electrons, and photons, forming a dense, opaque soup. But as the cosmos expanded and cooled around the 1 second mark, something pivotal happened. Neutrinos suddenly stopped interacting with other particles, decoupling from matter and flying free at nearly the speed of light. This moment, known as neutrino decoupling, froze their properties in time, preserving a snapshot of the universe's conditions in that critical first second before atoms, before stars, before even light could travel freely. What makes this background so invaluable is its unique vantage point. While the CMB reveals the universe at 380,000 years old, the neutrino background peers back to the very first heartbeat of cosmic time. These particles witnessed inflation's last tremors, the formation of the first atomic nuclei, and the universe's transition from a quark-gluon plasma to recognizable matter. Their energy distribution slightly cooler than the CMB due to an early episode of particle annihilation holds clues about physics beyond the standard model, including potential connections to dark matter or extra dimensions. Yet detecting this background directly is like trying to hear a whisper in a hurricane. Unlike photons, neutrinos barely interact with detectors, and their primordial signals are drowned out by more recent neutrino sources like the Sun or supernova. So scientists have gotten creative, hunting for indirect signatures. One approach studies the CMB itself. Those early neutrinos subtly influenced how matter clumped together, leaving faint statistical imprints in the cosmic microwave patterns we observe today. Another method examines large-scale galaxy distributions, where neutrino-free streaming suppressed the growth of small-scale structures, a cosmic fingerprint measurable in the voids and filaments of the universe's web. The most tantalizing hint came from the Planck satellite's data, which revealed a slight underdensity of galaxy clusters at certain scales, a discrepancy that aligns with predictions of how relic neutrinos should have shaped the cosmos. These observations suggest the combined mass of all neutrino species is around 0.06 electron volts, a featherweight by particle standards, but enough to leave gravitational ripples in the fabric of spacetime. Future experiments like Ptolemy aim to trap these primordial neutrinos directly using ultra-sensitive detectors chilled to near absolute zero, hoping to catch a handful of the oldest particles in existence. What's at stake isn't just a cosmic curiosity. The neutrino background could hold answers to why matter dominates over antimatter, whether sterile neutrinos exist, or even how gravity behaves at quantum scales. These particles are more than relics, they're time travelers from an epoch before atoms, carrying messages we're only beginning to decode. Every time a neutrino streaks undetected through Earth, it's a reminder that the universe's first second isn't lost to history. It's still all around us, hidden in plain sight. Stephen Hawking shook the foundations of physics when he revealed that black holes aren't the eternal prisons we once thought. They slowly evaporate, leaking radiation into space. But this beautiful insight came with a terrifying implication. If a black hole vanishes, what happens to all the information it swallowed? Stars, planets, even entire civilizations could fall into its abyss, seemingly erased from existence. This isn't just a black hole problem, it's a crisis that reaches back to the Big Bang's singularity, forcing us to confront whether the universe itself forgets. At the heart of the paradox lies quantum mechanics' golden rule: information cannot be destroyed. Every particle interaction, every chemical reaction is theoretically reversible if you have enough data. But black holes defy this. Hawking radiation, the faint glow that causes their evaporation, appears random, carrying no trace of the matter that formed them. It's like burning a library and claiming the smoke particles contain the patterns of every book. For decades, physicists assumed the information was truly lost until Lenny Susskind and Gerard T. Hooft proposed a radical solution. They argued that information isn't destroyed but scrambled across the black hole's event horizon, encoded in ways we don't yet understand. The surface area of a black hole, they suggested, might function like a holographic plate, storing data in 2 dimensions that only appears 3-dimensional to an outside observer. This idea didn't just rescue information, it bridged black holes to the Big Bang's deepest mystery. Both singularities represent points where gravity and quantum mechanics collide, where space and time break down. If black holes preserve information holographically, might the universe's initial singularity have done the same? Some theorists propose that the Big Bang's unfathomable conditions could have imprinted the seeds of galaxies, dark matter, and even the laws of physics onto a primordial horizon, like cosmic DNA compressed into a speck. The parallels are uncanny. Both scenarios stretch our understanding of reality, suggesting that spacetime might be emergent, a secondary phenomenon arising from deeper, information-theoretic layers we're only beginning to glimpse. Recent breakthroughs add fuel to the fire. The discovery of soft hair on black holes' low-energy quantum fields around their horizons hints at mechanisms for information retention. Meanwhile, experiments with quantum entanglement show particles remaining mysteriously linked across distances, a phenomenon that might mirror how black holes preserve data. These clues point toward a theory of quantum gravity, the missing link between Einstein's relativity and the quantum world. Solving the information paradox wouldn't just tell us what happens to a black hole's victims. It could rewrite our origin story, revealing how the universe encoded its own blueprint in the chaos of creation. The stakes couldn't be higher. If information is truly indestructible, then the Big Bang singularity wasn't an end but a transformation, a cosmic reset where the previous universe's data was scrambled into new physics. Alternatively, if Hawking was right and information can vanish, then reality itself might be fundamentally unpredictable, built on a foundation of cosmic amnesia. Every photon leaving a dying black hole carries this question into the void. And as we watch them fade, we're left wondering, does the universe remember, or is oblivion the final law? What if everything we perceive as three-dimensional reality, galaxies, stars, even our own bodies, is actually just a projection from information encoded on a two-dimensional surface at the edge of the universe? This isn't science fiction. It's the holographic principle, a revolutionary idea born from black hole physics that's now shaking our understanding of cosmic inflation and the Big Bang itself. The theory emerged from a startling calculation. The maximum entropy, or information content, of any region of space doesn't scale with its volume as you'd expect, but with its surface area. It's as if the universe behaves like a cosmic hard drive, storing all its data on an invisible boundary while we experience it as a 3D illusion. The connection to inflation is mind-bending. If the early universe underwent exponential expansion, as inflation suggests, then every quantum fluctuation stretched across space should carry holographic fingerprints, information imprinted not just in 3 dimensions but encoded on a 2-dimensional surface at the universe's horizon. Imagine blowing up a balloon with words written on its surface. As it inflates, the text stretches and distorts, but the total amount of information remains the same. Similarly, the holographic principle implies that the universe's entire history, every particle, every force might be recoverable from data compressed onto its boundary, like a cosmic Blu-ray disc playing reality in real time. This challenges inflation's traditional narrative. Instead of quantum fluctuations randomly seeding the cosmos, holographic cosmology suggests these patterns were predetermined by information flow from that boundary layer. Some versions of the theory even propose that inflation wasn't a purely 4-dimensional process but a shadow of interactions happening in a higher dimensional space, an idea reminiscent of string theory's brainworld models. When scientists analyzed the cosmic microwave background's fluctuation patterns, they found curious large-scale anomalies that some argue align better with holographic predictions than standard 3D inflation. The cold spot, those mysterious alignments in the CMB structure, could these be glitches in the cosmic projection, subtle hints that we're decoding a universe with hidden layers? Yet the holographic principle isn't just about rewriting origins, it's a potential bridge between quantum mechanics and gravity. In black holes, where the theory was first tested, it resolves the information paradox by suggesting swallowed data isn't lost but smeared across the event horizon. Apply this to the Big Bang, and the singularity's breakdown might not erase history but transpose it onto a new dimensional canvas. The universe's expansion, dark energy's acceleration, even time itself, could be emergent phenomena, side effects of deeper information processing at the edges of reality. While the math is formidable, the implications are tantalizingly concrete. If the holographic principle holds, future telescopes might detect subtle statistical deviations in galaxy distributions or gravitational waves that betray the universe's true two-dimensional nature. It's a radical reimagining of existence, where the vast 3D cosmos we inhabit with all its complexity and beauty is just the universe's way of rendering data from the ultimate projection screen at the edge of space and time. The next chapter of cosmic discovery is already being written, not in textbooks, but in blueprints for machines so sensitive they could detect whispers from the dawn of time itself. Leading this charge is CMB-S4, a next-generation observatory network set to scan the cosmic microwave background with 10 times the precision of Planck. Picture an army of telescopes stationed across the South Pole and Chile's high deserts, working in unison to map the CMB's polarization down to microkelvin fluctuations. Their prime target, the elusive B-mode patterns that could finally confirm inflation's gravitational waves. But this isn't just about sharper images, it's about peering beyond the inflationary veil. Some theories suggest these signals might encode relics from a pre-Big Bang phase, like quantum scars from a bouncing universe or collisions with other dimensions. Meanwhile, underground labs are preparing for a different kind of hunt. The Einstein telescope, a proposed gravitational wave detector with arms stretching 25 miles beneath Europe, won't just listen for black hole mergers. It's designed to catch ultra-low frequency ripples from inflation's final moments. Think of it like tuning a cosmic stethoscope to the universe's first heartbeat. These waves would carry direct evidence of how inflation ended, whether it was a smooth transition or a violent cascade of bubble universes colliding. The telescope's subterranean location shields it from Earth's noise, allowing it to sense distortions smaller than an atomic nucleus across interstellar distances. But the boldest experiments aim to recreate conditions that haven't existed since the universe's first trillionth of a second. The Future Circular Collider, a proposed successor to the Large Hadron Collider, would smash particles at energies high enough to produce hypothetical inflaton particles, the quantum fields thought to drive cosmic inflation. By studying how these fields decay in the lab, scientists hope to simulate reheating, the explosive process that turned inflation's cold expansion into the hot Big Bang. It's like reconstructing a cosmic crime scene, searching for forensic evidence in the debris of particle collisions. What ties these missions together is a single, profound question: what came before the Big Bang? Some theories suggest clues might hide in the CMB's statistical anomalies patterns so subtle they've been dismissed as noise until now. Others propose that gravitational waves from pre-inflationary phases could have left imprints at frequencies beyond our current detection. There's even speculation that neutrinos from the universe's first second might carry encoded messages about earlier epochs if we could just catch enough of them. The ultimate goal isn't just to fill gaps in our knowledge, but to test whether the Big Bang was truly the beginning, or just one transition in an eternal cosmic cycle. Future data could reveal whether our universe is a solo act or one performance in an endless multiverse symphony. With each new instrument, we're not just building better detectors, we're crafting time machines, piecing together a story written in gravitational tremors, quantum whispers, and the faint afterglow of creation itself. From the accidental discovery of the cosmic microwave background to the mind-bending possibilities of the holographic universe, these 25 breakthroughs have rewritten the story of our cosmic origins. We've witnessed how Arno Penzier's and Robert Wilson's persistent static revealed the afterglow of creation itself, a snapshot of the universe just 380,000 years old, still echoing across 14 billion years. Edwin Hubble's redshift observations shattered the illusion of a static cosmos, exposing an expanding universe fleeing from its explosive birth. The delicate dance of primordial nucleosynthesis showed us how the first atomic nuclei formed in a seething cauldron of particles, while the stubborn lithium problem hints at physics beyond our current grasp. Cosmic inflation emerged as the grand architect, stretching space faster than light could chase it, ironing out the universe's wrinkles and planting quantum seeds for galaxies. Yet its legacy is far stranger, perhaps a multiverse of bubble universes, each with their own laws, or collisions imprinting bruises like the enigmatic cold spot. We've seen dark matter's invisible hand sculpt the cosmic web and dark energy's relentless push accelerating expansion, turning the universe's fate into a question mark. The hunt for primordial gravitational waves continues to test inflation's wildest predictions, while the Hubble tension exposes cracks in our measurement of cosmic growth. From baryon acoustic oscillations frozen in time to the ghostly neutrino background whispering from the first second, every discovery peels back another layer of the cosmic onion. Stephen Hawking's black hole paradox challenged our notions of information and reality, while the holographic principle suggests the universe might be a projection from a distant two-dimensional edge. Future experiments CMB-S4's ultra-sensitive ears, the Einstein telescope's subterranean gravitational wave hunt promise to probe even deeper, potentially revealing pre-Big Bang physics or the inflattened field's decay. What ties these revelations together isn't just their scientific brilliance, but how they reframe our place in the cosmos. We're not just observers of the universe, we're its conscious particles, stardust threaded with questions, decoding light from the edge of time. Each breakthrough is a reminder that reality is stranger than fiction, and the next paradigm-shaking discovery might be hiding in plain sight, waiting for a curious mind to connect the dots. So keep looking up, stay wondering, and join us as we continue unraveling the universe's greatest mysteries. Hit subscribe so you don't miss the next cosmic revelation, because the story of everything is still being written and the best chapters may be yet to come.